Okay. Good afternoon, everybody.
Good afternoon.
Good, so it works. Yes. Let me just record the video. Stop pause recording. No, it's already recording. I see. Okay. So, good afternoon, everybody. We have the third class of Turbomachinery, the second class that I'm giving here. And today we are going to discuss, as you can see on the slides that I'm sharing, velocity triangles and conservation laws for applied to turbines. So you can see it here. Let me see. Let me just turn on this one. So you can see that the first part will be about velocity triangles. But anyway, before I start, just let me tell you on what I will discuss today. And then I will also ask a question related to previous classes. So conservation laws, Euler equation, and maybe if there's some time, I will also talk about design parameters. So these are pretty basic laws that will end up with a very important equation, which is the Euler equation. And the Euler equation is basically relates enthalpies or enthalpy changes across a stage of a turbomachinery and its velocity triangle. So its velocity is actually the inlet and the outlet. But before I will start with these topics, I will ask you, and you can also, of course, it's a bit more difficult now to do it online, but I have the chat window open so I can see questions that you will post. And I will also see if you raise a hand or so, hopefully, because I'm looking also to the other screens to see if you would like to interact with me. So what I will ask you a question is the homework assignment, the first homework assignment clear to everybody? I have seen, for example, some people already started with the homework assignment, and I also received, for example, one homework assignment worked out already. I received already one report. But if there are any questions, please let me know in the chat window, and then maybe I can answer the questions now if you have some. Otherwise, I will look at them in the break and then answer them after the break. I think the homework assignment should be available for, I think it's available. So there's one question, will the exam also, will the Excel sheet also made available for master students? I thought that it's already there, but maybe I would need to check again. I thought that Sike has uploaded both versions. For sure, there are both versions available on Dropbox for the external people. For the master students, I thought so too, that you would have the Excel. Do we hand in one document between the two people for separate? Sorry, there's okay. So the question is, do we hand in one document between the two people working separately? No, so it's if you hand in only one document, it's enough. You don't need to hand two documents in for each of the people that worked on one document. But of course, in this document, you should state both names and student numbers. Okay, so that it's clear for us who has been working together on this. So you only need to submit one report. Are there any other questions? Sorry, I had to mute GBO here because there was a sound problem. External students, do they have, no, you don't have student numbers. So you just mention the name and then make it clear that you are from external. And then we will also be able to distinguish it. Okay, you don't need to. Okay, so the Excel sheet apparently is not made available. we will make sure that they will be available also on Brightspace. Okay, you can use then Excel and MATLAB or whatever you want to do the homework, the first homework assignment. Yes, you can choose, of course. It doesn't need to be MATLAB. You can also use Excel. You can, or you can use Python if you want, or you can use any other languages that you want. Python will be actually more modern and more, yeah, it's also possible. So now, so Luke, I think we need to make sure that the Excel sheet is also made available on Brightspace for the first homework assignment. But now I will go ahead and I will start with this lecture where we discuss these topics here. And before we discuss velocity triangles in a turbomachinery, we need to make some assumptions, but we also need to make sure that our nomenclature is clear to everybody. So if we state some relative velocities, absolute velocities, if we say that the radial velocity, tangential velocity, or circumferential velocity, axial velocities, so that we know when we talk about these velocities, what we actually mean. And we have in the cycles, so when we discussed the cycles in the previous lecture, we always assume that the compressor is basically one piece, right? So we distinguish between a compressor which is made of infinite number of compressor stages, which gives you the polytropic efficiency, right? You don't know beforehand how many stages you will be using for a certain pressure ratio. But if you know that one stage has a certain efficiency, then we know that we need to have, for each of the stages, apply this efficiency, but the overall efficiency of the whole compressor actually will be very much different. Which depends on the pressure ratio and the number of stages, of course. And that's why we discussed the polytropic efficiency. But in general, we still thought of the compressor as a single piece, and the same for the turbine. But as you can see here on this picture, it's not just a single piece. We have for a compressor, for example, when the air enters here, so the air will enter here on this side, on this angular geometry, right? So it's a ring. And in this ring, you will have the air entering at a certain velocity or certain mass flow, basically. And then you will have, for most of the compressors, maybe not for all of the compressors, you will have something that is called an IGV, which is an inlet guide vane. And the inlet guide vane is used actually to create some swirl after this first part here. So here, in this location, you will have some certain amount of swirl. So you will actually create a swirl before you go into the first stage of the compressor. And the swirl is actually created in order to increase the pressure ratio maybe of the first compressor stage, or also can be used to control the mass flow, for example. Okay, so there are several ways that you can use an IGV. So there's the IGV is used for even regulating the mass flow, but also to create some swirl in order to increase the pressure ratio maybe for the first stage. But once you have passed the inlet guide vane, you will be here in this part, and then you can see that for the compressor, you have first a rotor, so a number of blades which rotate at a certain angular velocity, which basically adds angular momentum to the fluid. I will discuss this in more detail later. But you basically create from a purely axial flow, or let's say if you have if the IGV creates some swirl, but let's say the IGV doesn't create a swirl, then you have a purely axial flow direction in the inlet of the first stage. And what happens is that after you leave the rotor of the compressor stage, you will have created some angular velocity or tangential velocity, okay? And so you have added some work in order to turn the flow. And because of this turning the flow in the stator, you will be able to make this flow straight again, but by making it straight, you actually increase the pressure ratio. So as I said already in the previous lectures, a compressor basically consists of two sections of diffusers, right? A diffuser is something like that. One that rotates, and another diffuser part, which basically is stationary, and it's called a stator. But so one diffuser, the part rotates and the other one is stationary. So you have first the rotor and then the stator. Then if we go to the turbine, you can see here in the turbine, we have the opposite. We have the stator first and then the rotor, and then we call this one a turbine stage. And In the turbine, you have first the rotor, and the rotor again now creates angular momentum. So you add tangential flow velocity, and this tangential flow velocity can then be used to extract work from the flow. Or let's say the work is actually passed then to the rotor blades. There on the slides, you can see it's a link. The IGV is stationary. There's a question, is the IGV moving or the IGV is stationary? Stationary. Okay. And the IGV does not move. You can rotate individual blades. So you don't rotate the IGV, but each individual blade maybe of the IGV can change its angle. Okay. It will not rotate. The U velocity, circumferential velocity will be zero. Is the rotor rotating the same speed as IGV? IGV is not rotating. And the IGV, of course, the IGV can be also used, of course, to change the mass flow. By mass flow, you go into off design conditions, off nominal conditions is written here. And so, which means by changing the mass flow, you go from off design conditions. And nowadays, all of these turbines actually have to be able also to operate in off design conditions, not at 100% load, but maybe at a lower percentage of load, 70%, 80% load. If maybe electricity is not used or not necessary at certain periods of time, because you get a lot of electricity from renewable energy sources like wind or solar. And when they provide a lot of electricity, then you actually want to turn down the gas turbines, or not turn down, you reduce the load of the gas turbine so that the gas turbine is not providing 100% of its capacity. And that you do with an inlet guide vane as well. So you can change the mass flow with inlet guide vanes, and then there are certain other tricks that you need to use in order to still keep the efficiency of the gas turbine high. Of course, the highest efficiency is probably going to be at design condition of 100% at full load. But if you go to part load, the efficiency significantly drops. But there are also several possibilities to keep the efficiency at part load still high. There's also research done right now on these topics. And I think Sike has mentioned this also. So a lot of gas turbines nowadays are used as peak shavers, right? So you get electricity, but then you need to provide a certain amount of time. You need to provide a lot of more electricity than you actually turn on the gas turbine to provide that amount of electricity. Then, so when I talk about nomenclature, then you can see that we have here several reference frames. We have a reference frame here and its notations. So when this is what you see, for example, here, this is polar coordinates or cylindrical coordinates that we are going to use. We have X, which is for the axial component. Then we have an R here for the radial component. And of course, we have theta, okay, for the tangential component or circumferential component. Then you can see here, this is a cylinder surface, right? And which we also most of the time use a cylinder surface. And for most of the turbo machineries that we are going to look at, because we are going to look at only mean design analysis, let's say, and we are going to neglect a lot of effects that happen in this first stage. One of the effects that can be neglected is that we can say that the radial velocity, for example, is zero. I will discuss this later. So there's no radial component. The flow basically is only on this cylinder plane, right? This is the cylinder plane here. And so we say that at the beginning, at different stages also, you can say that the flow is purely two-dimensional and that we have no radial velocity, for example, and which means that we only have an axial component of the flow and then, of course, the tangential component of the flow, C theta. And here you would have a blade, right? So here you would have a blade sitting on top. I'm not sure if you can see that's something like that. Then also you can have the frame of reference can move or it can be stationary. So if I'm standing outside and I look at this turbo machinery, a rotor is in a stationary frame of reference. But then I can also say I can also step on top of the rotor. So I see a rotor blade and I step on top of the rotor blade. Then I'm moving with the rotor blade, which means that I'm in the relative frame of reference, which means that I'm they're seeing different velocities because I'm moving with the velocity, with the rotor, and then I basically do a Galilei transformation. We can discuss this in more detail. But it's quite simple in this case. So we have a relative frame of reference when we move with the rotor. And so what we do then is that most of the time we can split the velocity into two parts. We can, if we are moving with the rotor, we can call the frame, the velocity which we see when we sit on top of the rotor, we call it relative velocity. Then of course we have a certain speed with which the rotor moves, which is the rotational velocity. And then we have the absolute velocity here. And so when I do this, most of the time I will call the absolute velocity with a C letter, relative velocity with a W, and the blade speed for the rotor with a letter U. Okay. Also in the book you can see this definitions this way, that you have C is equals W plus C is equals W plus U. Some of the books, some of the older books especially, might have different definitions where depending on how you define the vector itself, you can have a minus here or plus, okay? But we are going to do it always like that the absolute velocity is nothing else than the relative velocity plus the velocity of the blade itself, okay? And so that's what we said, the absolute velocities, but we also have absolute angles, which you see later. Absolute angles are called alpha, and the angles in relative frame of reference are called beta. And the velocity, not omega, W, not omega, W. And so what are the assumptions that we can make for turbomachinery? We can say that the radial velocities are negligible. Of course, if you look at the real turbomachinery with look at the flow speed and you look at the blade shape. The blade shape is maybe a twisted blade, maybe highly three-dimensional. And because of that, they are actually trying to improve the efficiency of each compressor or turbine stage by making the blade three-dimensional. And what they want to do with this is, for example, to reduce secondary flow effects, okay? Secondary flow effects are, for example, the radial velocity. You can have velocity not only being two-dimensional on the cylinder plane, but there can be also a component that actually is in radial direction, which you don't want because it contains kinetic energy that you actually lose. Then constant midspan radius. Yeah, so we assume also that we have the midspan radius is constant. So let's say if this is a shaft and this is the axis, and you have here for the compressor, the rotor blade, let's say, and then you have the outer casing, and then you will have here a stator. This is the stator, if this is a compressor stage. Then you can see that when I talk about midspan radius, this coordinate here, this coordinate is called the span, okay? And the span goes from R in to R outer radius. This is the inner radius, and this is the outer radius. And if I call midspan, then I'm exactly in the middle of it. This plane here is called midspan. So I say that we have a constant radius at midspan, that the radius here doesn't change as we go through a stage, okay? Which means it's very easy to unwrap this surface, such a cylinder. And this also applies, since the radius is not changing, the blade speed of the rotor here and here will be the same, right? The rotor rotates with a certain angular velocity, omega, right? Which means that if we are taking the velocity here, blade speed u1 and blade speed u2, since they both have the same radius, the blade speeds at inlet and the outlet of the rotor are the same because the radius constant is constant, which means that this applies constant blade speed. We can unwrap the cylindrical surface onto a two-dimensional plane. It's pretty basic. So these are the things that we need to agree upon when we start talking about velocity triangles. Now, let's start with the turbine stage. You can see here, how does a velocity triangle for a turbine stage look like? And it's, many of you have probably seen it, but I will go and discuss this in more detail today. So you can see that this is for turbine. We have first the stator and then the rotor. And the velocity, we can assume here is a combustion chamber somewhere, right? Combustion chambers, and the air comes out like this in the axial direction. And so we have a velocity, which is this one here, C1. Okay, so this is the velocity, the absolute velocity C1, and the stator is not moving. So what will the flow do? Basically, the flow will follow the camber line of the vane. And it's also something important. So this guy, as for the rotor, this guy I call it blade, and this guy I call it vane. Okay, it's not a blade. Blade usually is for the rotor, which moves. For the stator, it's a vane. And the camber line is this middle line here. And so if you assume that we have no losses, no flow separation, no boundary layers that build up along the stator blade, then we can say that the flow is simply going to behave like an Euler fluid, right? And it will just follow the blade angles. The flow goes in here, and it will just follow the blade angles. It's obvious, right? So the outward flow velocity will be something like C2. And you see what I did already here. So the axial component is X. And here I could also say I have an axial component here. Cx1, and this will be C theta 1. Okay, Cx1 and Cx theta 1. Right? So I've decomposed my C2, absolute velocity, into two components. And so what you can see here is that if the density and the area, the cross-sectional area here, the inlet and the outlet of the stator doesn't change a lot, and the density doesn't change due to mass conservation, I already know that C1 has to be the same as Cx1, but this is not the case in many turbomachineries, not for compressor turbomachineries. But anyway, now I do it like that. So now you can see that I have this part here. Now, how does the velocity triangle look like for the rotor? The rotor here will have a certain blade speed u, right? It moves in this case from down to up. It is a certain velocity. And then you can see that if I use my equation, which is C is equals W plus U, okay? Then I can see that I will be able to get my W velocity by simply saying C minus U. Okay, these are vectors. I can specify vectors like that with the line underneath, or I can put the vectors also like we learned in middle school with a vector on top, whatever. Usually we can also be more precise, and then we can use underline, and then for matrix we use double lines. But in this case, these are vectors, so you can easily see now if my u is given. If I know my u, then I can easily calculate my w, and in this case, my velocity triangle will look more like, for the rotor, more like that. I have an inlet. Yes, I have, this one is my u. No, sorry, let me do it differently. You can see it this way. So you can see that I have C is equals W plus U, and these are vectors. And then you can see that this C is equals W plus U. So now I know my relative velocity at the inlet of the rotor, which is W2. And so you can see here the way I drew it, and I should maybe make it in red. You can see that this here is W2. So W2 is this guy here. And you can see it should be parallel to the camber line of the blade here, right? So this is the camber line, and the camber line basically here should be parallel to, the velocity should be parallel to the camber line of the inlet of the rotor, right? And so then you can see that I have my W2 vector here. And so the question is now, how will the velocity look like at the outlet of the rotor? And of course, the velocity in relative frame of reference will again follow the blade angles. And then I will get a W3, which is this one here. And then I got my W3, my outlet vector. And if there are no losses, the velocity should really follow the camber line or the blade angles. If the flow behaves like an inviscid medium. And then I use again my equation, W plus U, which is this blue U here. Now this is my U, and then I will get Oh, sorry, it should have been yellow. Fine, and then I get my C3. C1 and C3. So you see, I went through the rotor and you saw that I get basically in the stator, first I create angular momentum. That angular momentum means I have a lot of swirl, and this swirl is then converted slowly into, is slowly extracted in the turbine. So power is produced by turning that flow again into axial direction, right? So now you could ask yourself, how come that this turbine has produced work and extracted work from the flow, but the velocity C1 and C3 are the same? Something must have changed, right? I will ask a question, I think, in the next slides. Let me see. So it's weird, right? You have the velocities, all of a sudden you see that the velocity at the inlet and the outlet is the same, but still you were somehow able to extract work. How can this work? How is this possible? And what I did here is that I didn't say anything about how the density changed and the pressure changed, right? Density and pressure must have changed. Otherwise, how can I extract work from such a turbine? And you will see it here now, right? So if I go continue with this, you see it here. And now I can ask the question to you and try to use, so if you just use your smartphone, open the camera and hold it towards this symbol here, towards the barcode, and you should be able to see a question in Google Forms. And then the question to you is now, this one here, right? It's an important concept here. Which angles are a function of u? So you have seen that what happens if the flow goes through this turbine stage, but the question to you is now, let's assume that the inlet flow velocity is constant. It doesn't change, but what is changing now is the velocity u. The u velocity, the rotor speed is changing. Let's say I have a faster rotational speed or a slower rotational speed. The question to you now is, if you look at these angles, which I didn't mention before, as I said, in the absolute frame of reference, I use alpha, and this is the angle alpha with respect to the machine axis. This is alpha, this one here. This is alpha 3. In this case, alpha 3 is equal 0. In beta is the angle of...
sorry, may I interrupt? The screen is frozen.
Oh, sorry. Now?
Yeah. Okay. Thank you.
I'm sorry. Okay, if I go away, then it freezes. Okay. If I go away, if I go to another desktop, it freezes apparently. So what I wanted to say, if you scan this symbol here, this barcode with your smartphone, then you Google Forms will open with a question, and the question is, which angles are a function of u? And what I was just saying is that if you assume that the inlet velocity stays constant, right? So this is our constant. The mass flow is constant of a turbine. I fix the mass flow rate through the turbine. But what I do change is the rotor speed, u. Let's say I increase it or decrease it. I increase the shaft speed of the rotor. The question now is, which angles do change and which angles stay constant if we assume that we have no losses in this turbine? The angles are alpha 2 is the angle between the absolute velocity and the machine axis, this one. Beta 2 is the angle between the relative velocity and the machine axis. Beta 3 is the outlet relative velocity of the rotor and the machine axis. This is beta 3, and this is alpha 3. Alpha 3 in this case is 0. The question to you now is, which angles are changing as a function of u? Let me see if you are participating here. Yes. Okay, still wait a bit. Now I have 29 responses now. Which you should be able to see here. Oops. You should be able to see now the screen with the responses. Yeah, so I think there are 59 people actually logged in on Zoom. I have 40 responses, so actually it's quite well. It works quite well. I will wait for a few more seconds and then I will go ahead. I hope the question was clear. Which angles do change if I change the rotational speed? The QR code again, yes, the QR code. Okay, so I will go back to this and share it with you, which is this one here. Okay, 49 responses, and the answers were, which angles are a function of u? And you were saying alpha 2. You see, so the gray bars are the wrong answers, and the correct answers are alpha 3 and beta 2. So the correct answers actually are the one with the least answers. Okay. So now in a real classroom, we could I could ask the people who answered the green bar, who gave the green answer. So who said that alpha 3 is a function of u and beta 2 is a function of u. I could ask you to explain it to your colleagues on why you think this is the case. Let me go back to the slides now. And then I will explain it to you. So actually, most of the people said beta 3 is a function of u. But I said that clear pen markings. So let's say that I get a green velocity now. I say that, let's assume that my u velocity is increasing. So my rotation, maybe green is not good here. Let's say black. So let's say that this was the initial velocity u, and now I increase the velocity and I make this velocity u. So I say my rotational speed increases, my blade speed increases, and if my blade speed increases, what happens? Alpha 2 remains constant because alpha 2, the float simply follows the blade. If u has increased, u goes down this way, and now it's longer, which means that my beta 2 has changed. Beta 2 here is 0, and here beta 2 would be smaller 0, right? Beta 2 is a function of the blade speed u, which is one of the good answers. Then we continue. You will see what happens. Of course, if you increase the rotational speed, what happens is that the relative velocity of the rotor will do something like that, right? It will not hit the nose anymore, but more the suction side. And this thing is called the suction side. This is the suction side, and this is the pressure side. So the flow will hit the suction side here. And then if you think of a flow that would probably do something like that, you will see that you will get separations here, right? You will get separations on the pressure side if you increase the rotational speed, if you have losses, of course, and if you have viscosity in the flow. But anyway, afterwards, you can say, okay, the flow will have flow separation here, maybe, since the flow comes this way, then you will have flow separation here. But afterwards, the flow will simply follow the blade speed, but in relative frame of reference, which means beta 3 will not change. Beta 3 stays constant. We will have this one here. But since U has increased, U will be here now. This is my new U. And then you see that alpha 3 has been initially 0, and now it's positive. And now this is my new C, C3 prime. And this is my W2 prime. So my W2 prime and my W2 has gone from W2 to W prime, and my C3 is become C3 prime, which means that beta 2 and alpha 3 are a function of the velocity. Clear? I think it's pretty clear. Now, I promised you before, so I was saying that it's weird. You see the velocity C1 is the same as velocity C3, so but still I will be able to actually get some work out of the turbine. How do I do that? And the way to do that is the following. Let me go to this one here. Yeah, this can take a lot of time now. So, but it's a very important concept also. So let me do it slow for the rotor then, and we can do a bit faster this whole procedure also for the turbine. So in the next 8 minutes, I will explain detailed entropy diagram for the rotor. Sorry, I've rotated now this turbine stage. You can see this first part here is the stator, right? This is the rotor here. The rotor has a certain velocity, and we saw the velocity triangles just before. Okay, so this is the absolute velocity that comes in C1, and let's say here here would be C3. Okay, I just rotated it by 90 degrees, this figure. And what I want to do now is I want to draw the HS diagram. This is entropy, and that can be enthalpy, or as we said already last time, you can just have a factor Cp in front of it if you assume it's an ideal gas and a calorically perfect gas, which means Cp is not even a function of T, but Cp is just a constant value. Then you can assume that the H axis and the T axis are the same, just scaled by Cp. Now, let's take this point here. This is point 1. So in a turbine, usually I have a high pressure at the inlet, which means that I will assume my point 1 being here. Okay. This one here, and this is point 1. Now I have a certain velocity here, and we know from the definition that the total enthalpy, right? The total enthalpy is nothing else than my static enthalpy, or my sensible enthalpy in this case, plus the kinetic energy. What is the kinetic energy of this flow? Nothing else than c squared half. This is the kinetic energy of the flow. So if I want to know the total enthalpy, and we have seen this from the first law of thermodynamics for open systems, which I don't need to write it down here, but you know that we have defined the enthalpy first of all, because we are using open systems, and the enthalpy we know is nothing else than U plus PV. It's not that we define this just by some arbitrary reasons. No, it's because this enthalpy will show up in many definitions, in 2 definitions mainly, which is the definition of how much heat do I need to add to a closed system when I keep the pressure constant, which gives me my Cp value, Cp, and Cp is nothing else than the partial derivative of enthalpy with temperature along constant pressure. And then, in fact, what happened in the beginning is that we didn't get such an equation, but we got the partial derivative of the internal energy plus the pressure plus the specific volume, the derivative of this term with respect to temperature, but along an isobar, right? Along an isobar. And so that I don't need to write this all the time, because it's tiring to write this all the time, U plus PV, we have just introduced a new quantity, which we call enthalpy, okay? And then if we derive the first law of thermodynamics for an open system by using the first law of thermodynamics for a closed system, we will see that we again end up with enthalpy. We will again end up with U plus PV. So if I talk about first law for an open system, then I again use not the partial derivative, but the total derivative of the energy for my control volume. I have a control volume. In this control volume, I have some flows coming in, and I have some flow maybe going out. And across the boundary here, I would have maybe some heat addition, Q going in, and maybe even worse, more complicated, I might have some turbine wheel here that will also extract some work. And then I also have some work going out, right? And so if this is the red thing is my system boundary, and this is called my CV, my control volume. For closed system, I talk about control mass. For open systems, I call control volumes. And then I end up with an equation, which is dt equals Q minus W, which is very similar to the first law for a closed system. But now I would have plus mass flow in times enthalpy plus kinetic energy plus something else, most of the time also potential energy minus mass flow out with enthalpy C1, C in, and C2 plus G, C2, 1, whatever. Plus whatever, you can have a bunch of stuff in the energy equation. You can also have heat source, you can have combustion, you can have whatever you want. But as you can see, if for a stator, for example, and we are talking about a stator and we talk about steady state conditions, then the internal energy in the control volume is not changing anymore if we have a steady state condition. We have a turbine that has been operating for many hours. If you take a point inside the turbine and we look at its pressure and temperature, we will see that they will not change on average. That means that there's no time derivative, zero. If we have a turbine that is perfectly insulated, so we put a humongous blanket across around the turbine, and we make sure that there's no heat exchange between the turbine, the flow inside the turbine and the outside, then we have this one zero. In the turbine, we will have a certain W, so this is not going to disappear. But then, of course, we have a mass flow in with a certain enthalpy and kinetic energy, and that's why we introduce the total enthalpy. This is the total enthalpy. Okay. Okay, this was a small excursion, but I need this in order to explain where to find the total enthalpy in the system, which means that this one here is C1 squared divided by 2. The kinetic energy at the inlet gives me the total condition at point 1, which means this one is H total 1, and this will be H1. And then I will have here relate for the HS diagram, of course, I will have here a P0, 1, the total pressure at the inlet, the total enthalpy at the inlet, which is this one here, and of course, total density, anything, because I have a HS diagram, I know two thermodynamic quantities, the total pressure, total temperature, and I can define my point in the thermodynamic plane. If I go down this way, I take this equation and I want to know what is my static temperature and static pressure. It's nothing else than the 0, 1 minus the velocity, kinetic energy, which is this part here, minus the kinetic energy, total energy minus kinetic energy gives me this point here, number 1. And now we know that this point here is P1, static pressure, and this point here, static enthalpy or temperature, T1. Now I'm here. I still didn't move through the stator. And now I go inside the stator. And if I say that the stator, of course, will have a boundary layer here that will build up. Boundary layers, it will be laminar. And then at some point it will be turbulent. Maybe you get flow separations, you get a wake. Here you will have a wake. You might even have shock waves if the flow is transonic, which introduces losses, which means that from here, point 1 to point 2, I will increase entropy. My entropy will increase. Some of the energy in the flow will actually be just converted into increase of entropy. So I go down somewhere this way. If it's insulated the turbine and I don't have a heat flux, this can never go this way. This is very much wrong. It cannot happen. I can only increase entropy. I can never decrease. In an isolated system where there is no exchange with the environment, entropy can always only increase, never decrease. And I will end up somewhere here maybe, right? So this is my point 2 now. Let's call this point 2. Point 2. And now you can see here that I go from point 1 to point 2. My C2 has increased. So the kinetic energy at the outlet of the rotor has increased. So I see this point here is now my C2. C2 squared half. And this guy here is C1. And I end up, if I know the losses, if I know the amount of losses I will generate, if I know how much my flow speed will increase from here to here, I will know my second point. I know my static pressure at point 2. This is now P2. And this guy here is T2. Right? And now we're already in the break. Let's have a break and then I'll continue with this one. Okay? Let's have a break for around, let's start again at 4:45. Okay, now it's 4:32 and we start at 4:45. And we have a break of a couple of minutes. And then I continue with this. Yes, let's get coffee. Okay, let's go ahead. There's a question, I know, but Luke, I think you replied already. The question is, why does the total enthalpy in the stator from 1 to 2, why does the total enthalpy from point 1 to point 2, why it doesn't change, right? It's very important to get this right. Not sure if I should reply to this again or should I explain it? Why is the enthalpy, the total enthalpy from point 1 to point 2 not changing? Should I, hands up if I should explain this, otherwise I go ahead. Maybe I explain it anyway, while I explain the other things. Okay, I get a few people saying that I should explain. And I had it before already, I write it quickly again. So the first law for an open system is this one here, right? Is Q is the heat transfer across the boundary, the work transfer across the boundary plus mass flow in times enthalpy plus kinetic energy minus the mass flow out times H plus C squared half. This we call total enthalpy, and we call it 1, total enthalpy. And usually what I do is total enthalpy is with a 0. So the total conditions are indicated with a subscript 0, or we call it H naught. Okay, H01 is the total enthalpy. At the inlet, total enthalpy at the outlet, the mass flows are the same. If it's steady state, this is 0. Across from point 1 to point 2, the stator is not moving anywhere. The stator is stationary, which means that there's no work that can be extracted by an axis. There's no axis pointing out from the stator, right? So from point 1 to point 2, the flow just goes through a stationary guide vane, which means that the work is also 0. Now I make the assumption, which in fact for gas turbine is not true. And the smaller the gas turbine, the higher this effect is for turbochargers, for example, in cars, or for very small gas turbines. Then the small gas turbine, yeah, you need to be careful. Also, the area, of course, has an influence on the heat transfer rate, right? The larger the area, the larger the heat transfer. So you need to, there's a trade-off between the heat transfer within the turbomachinery components themselves, but also with the environment. So what you have is that if the temperature in the stator of a turbine is very high, much higher than the environment, the temperature at environment, then of course you have heat losses. And heat losses means that you are effectively cooling the flow from 1 to 2, right? Cooling would mean decrease of entropy in this case. And you will, if you get to the same pressure ratio, then you will end up actually somewhere here at this point, okay, without going too much into detail. But let's assume that there's no heat transfer across the stator with the environment. Then Q is also 0. Then what the equation that remains here is the mass flow rate times H01 is equals mass flow rate H02. Since the mass flow rate is the same at the inlet and the outlet, we have mass conservation. We can simply say that mass flow H1 is equals H2. Stator only. Okay. This is only applicable for the stator because I'm going to discuss later the Rotalpy, which is then applicable to the rotor. So now I have this thing here. So now I go from this, from point 2, this point here, which is here. I have no pressure to and I have no temperature to. So I have, basically it's just a nozzle. So I've accelerated the compressible flow. It's a compressible flow in this case. So I've accelerated the flow, which comes with an expansion. The pressure decreases and density decreases, temperature decreases. And then I'm at point 2. Now in point 2, I go inside the rotor. And now it becomes a bit more complicated in the rotor because the rotor usually also will expand the flow. It's a nozzle. The rotor is a nozzle, but in rotating frame of reference. Okay. So I go from this point to this one here. Now I'm pressure 3. Now this is P3. And if I want to know the total conditions at the outlet, what do I need to do? I need to add C3 again. So I add C3 here, which is this one here. This is C3 divided by 2. It's my kinetic energy at the outlet of this. And then I get my total condition. Pressure 0, my 0 indicating total condition, not 3. And then I'm here at this point. And so a very important thing that you will see later when I use the Euler equation, and we can go faster through this, you will see that this part here and this part is my delta H. 0 is equals H01 or 03 minus H01. And this is related to the power that can be extracted. Power. If I multiply it with the mass flow, the delta H with the mass flow multiplied, it gives me the power. Otherwise, it's specific work in this case as well. Okay, so but the thing is now, how does this work in this case? Okay, so this is a HS diagram now for this stator. Sorry, for the rotor, for the turbine stage here. But the nice thing about the total enthalpy before was that I can say that the total enthalpy from here, H total, is constant if I have it, if there is no heat transfer across the boundary. But what happens between 2 and 3? I can apparently not say that the total enthalpy is still constant, because you can see that the total enthalpy has decreased from here to here. This is my H03 and this is my H01. But across the rotor, I should also be able, let's say if I say across the rotor there's no heat transfer with the environment, so I'm perfectly insulated, then I should be able to also state something similar to the total enthalpy. Okay. And the way I can do this is by defining the Rotalpy. And then delete. Stator H01 is H02. Rotor, I can say in the relative frame of reference, I can say that my H2 plus kinetic energy in the relative frame of reference is equals H3 plus W3 squared half. Now this one is the kinetic energy, the relative frame of reference, right? My W here is when I move with the rotor, which means it's relative frame of reference. This velocity is W. H2, of course, is the static enthalpy. But then what I need to make in this case is that I need to subtract a kinetic energy of the frame of reference to make it consistent. I have this minus 1/2 U squared, minus 1/2 U squared. So this basically is the total enthalpy now, as you can see, but in a frame of reference that is moving with the rotor. So if I derive this thingy, then I can say that the quantity that stays constant, across the rotor is my Rotalpy, which is defined usually as an I here, and we call it that H plus 1/2 W minus 1/2 U squared is equals constant. So now I'm able to actually also draw the velocities in the HS diagram. And that's what I want to do. So if I use this equation here, then I will be able to get from point, I will use a different color now, from point 2, I can draw here, up here. This is my W2 squared. Since my blade speed at the inlet of the rotor is the same as the blade speed at the outlet of the rotor, this is 2 and this is 3, the blade speed is not changing. We said we are along a constant radius, and this can drop out, so I don't need to worry about that stuff here. And then I have a line here, which is I equals constant. And then I can draw the point here, so this line here, and then this velocity here. Is my W3 squared half. The same thing as in the stator, just in a relative frame of reference. Before, I was using absolute velocities. Now I'm using relative velocities. Okay, this rotalpy across the rotor stays constant if you have no heat losses. And this can be very useful also for analysis and actually also for, you can derive it in many several ways. So there's a question how, the C3 should be a squared. Yes, not cubed, of course. 3 should be squared, and here should be a 3. The other question I have is how is the rotalpy defined? The way I define it very simply here is by just saying that take the enthalpy at the relative velocity, because you're moving with you're on the relative frame of reference, and on the relative frame of reference you have a relative velocity. So the kinetic energy basically is from the relative frame of reference, and then I subtract a velocity which is a fictitious kinetic energy of the frame that moves with a certain speed. You can derive it like as simple as I did it here, but you can also do it more complicated using the Euler equation, which is derived later. But it's given in the book that Siegler-Klein also mentioned in the first class. Dixon and Hall has a more detailed derivation of this rotalpy. But remember, across the stator, if there's no heat loss, the total enthalpy stays constant. Across the rotor, the rotalpy stays constant. The rotalpy is also a quite important concept, because now I'm talking about axial machines. This is an axial turbine or axial compressors. But if you have radial machines, then this concept of rotalpy can be actually used in order to increase the pressure ratio. Axial compressors have a low compressor ratio compared to radial compressors. Radial compressors, you see them, for example, in helicopter engines or also in turbochargers. You can see a compressor, a radial compressor, and a radial compressor has a much higher pressure ratio than an axial machine. The same for turbine. And the reason for that is because U in a radial machine, U is not constant. And that, guys, are used then to increase the pressure ratio. I will discuss this later. Okay, and then we go to the slides. Messy slides here. No, this is fine. This is what I have here on the slides. So I have derived it now on this notebook, but here on the slides you have it again. So this is the definition of the rotalpy here, and it says this I here is constant along a streamline through a turbo machine. You need to define a streamline, and the streamline can only be defined if you have actually no losses or no turbulence, let's say, expressed in terms of total enthalpy, and then you can derive all of this stuff here. Okay. Clear? In the slides, you can again see the HS diagram. I did it stepwise, but you see the same thing here also in the HS diagram. Okay. Why is W not squared? I guess a typo. Where is W squared? Is there on the slides? There's a square here, there's a square here. In Rotalpy. Okay. Maybe I made a typo in this equation here. Oh yes, this is a typo. Very good, very good. There should be a squared. Nice. Nice, okay. So then, how does it work for compressor? And I will go a bit faster now. So for the compressor, we say that we look at this part here now. So why did I do the HS diagram? What was the reason for it? Well, as you will see later, is that I can simply make a connection between the change of enthalpies with the velocities of the stage. And I've done this now for the turbine stage here. You can see here the combustion chamber, right? In this turbine stage here, you can see the vanes. These are the vanes. And you can see here the rotor, and you can see here the low pressure turbine, again, vanes. And you can see there's already some swirl in the flow. And then you can see the rotor again. But I can also do the same also for the compressor. But as we know, the compressor has first the rotor and then the stator, because I want to add work to increase the pressure. And I don't want to extract work by expanding the flow. And so I have the rotor here. Again, I use the same equation. C is equals W plus U. I mean, probably you have already seen this in other classes, also in the bachelor. This is discussed already. Maybe not so much in detail with the HS diagram, but the rest is, I think, discussed. So you can see, again, if I know that this is the rotor and the compressor will move this way, this will be my U velocity. And since I know that U plus W should give me my C, I will see that this here is my W. And then I take this, and then you can see here W1. Then I continue. This is this guys here. Then the flow again moves with the blade. So this is the camber line of the rotor. The flow, if there are no losses, just simply follows the blade angles. Then you get W2. If I add the circumferential part to W, I get this one here. I add my C velocity here. And so now what you see here is that I have let me continue. So now you can see that I have a certain angle here, right? This is the stator now. And so I go through the stator, and if there are no losses, again, the flow will just simply turn, and I will get a velocity at the outlet. But what do you see here now? You see that in the absolute frame of reference for the stator, you see that at the inlet, I have a large kinetic energy. C2 is larger than C3, right? If you think about the Bernoulli equation, what does this mean? Here I have large velocity, low pressure. Here I have low velocity, higher pressure. The pressure has increased here. But if you look at the relative frame of reference for the rotor, you can see here inlet velocity W1 is larger than W2. So yeah, you see here W2, which means that the pressure has increased here in the rotor as well. So I have two diffusers basically that increase the pressure, first in the rotor and then in the stator. Okay, and that's how a compressor increases the pressure, because I add momentum to the flow in order to increase the pressure here. Okay. Now, this is what is written here. So you can see that compressors use rotors to create a moment of momentum, and which is then removed in the stator to create further pressure rise. You can do the same story also for the compressor here. Again, derive a HS diagram in very much detail, but for the compressor, it's a bit more complicated because you need to start with the Rotalpy. Again, you see here, You see here the total condition at the inlet. Of course, the total pressure at the inlet is lower, right? It's this one here. This is the inlet, 1. We have a low total pressure, let's say ambient conditions, total pressure of 1 bar and total temperature of 20 degrees Celsius or something. If the flow is, the flow speed is very small, then of course you have a C1, which is this one here. And then we go and derive static pressure here, which means this is 0.1. And then you do the same thing with the Rotalpy. You again add to the static enthalpy at the inlet the relative velocity, which is this one. Then you arrive here at this I. This I stays constant across the rotor. You subtract W2 to arrive at 0.2. And from 0.2, you basically can already derive or find the point P03, which is this one here. This is P03. And so maybe I didn't explain this before in a nice way, but you can see that if you have losses across the stator, you increase entropy, right? This is entropy increase from here to here. This is delta S. But this delta S is very much linked with pressure ratio. Okay, this is pressure loss. Total pressure loss, which you can see here. This is P02 and P03. This total pressure loss here is related to delta S. Okay, so delta S and the total pressure loss are very much related to each other. And you can see in an HS diagram also how much pressure loss you have. So if you know the pressure loss across a certain turbine stage, if you measure the total pressure here, and if you measure the total pressure here, then you will be able to actually identify the entropy that you have generated and the losses that you have. These are now axial. So before I was talking about axial machines, and this is a radial machine, and this could be, for example, a radial compressor, as you can see it in turbochargers, right? In this case, but I will go a bit faster ahead in this one. And now let me come to the second point, is how do I now define the conservation law, or how do I get to the Euler equation? And for the Euler equation, I need to use conservation laws. So we have seen the HS diagram for the compressor and an HS diagram for the turbine. In there, we know that we have velocities and we have enthalpies. And the Euler equation is establishing a relation between delta enthalpy and the velocities. And this is what is done here. And I will show you quickly, very quickly now, how this is done. And what conservation equations do we know? We know 3 conservation equations for us that we need to know here is conservation of mass, conservation of momentum, and conservation of energy. And for those of you who are following advanced fluid mechanics, you have seen these equations now many times already. And the first equation in integral form is this one here for the conservation of mass. A bit more complicated written, but in integral form, and if it's steady state, again, this guy is 0. If nothing is changing in time anymore, if I hold the measurement probe here and I record stuff in time and this value, it doesn't change in time, that means that it's steady state and I have no derivative in time, which means this term is 0. So the only equation that remains for the conservation of mass is nothing else than in integral form. C, I have bold letters here for C, and for N, C is a vector here, N is the normal vector. This one here, always outward pointing, it's a vector. N is here. You know, N is also here, of course. And N is also here. It's a bit more complicated, but it doesn't really matter. You can make it complicated or not. This one here. So these are all my normal vectors, right? And this is my control volume. This guy here is my control, control volume, CD. I use for open systems always control volume. For closed system, I use control mass in thermodynamics. But this is a control volume. And this here is, for example, the stator. So whatever mass goes across this interface or this surface here will also enter or go out here. So you can completely neglect what happens on these surfaces here. The only surface you need to know about is this one here. And so how do you calculate the mass flow here at the inlet? Nothing else than if you have a velocity, and the velocity might even be something like that. Oh no, it's not good. The velocity might be something like that. C1. Then you take the dot product between velocity and normal vector, multiply it with density and area, and you have the mass flow, which is this one. What I want to say with that, it's very important to always take for the mass flow calculation, of course, the velocity component that is normal to the control surface, right? You have seen this. But the mass flow in is equals mass flow out. There's no mass that disappears or that is generated somewhere here. Now, you can go to the next conservation equation, which is the conservation of momentum. And so I take the conservation of momentum in integral form, a bit more complicated, but you have derived this in advanced fluid mechanics. Again, if it's steady state, this can be zero. So nothing changes in time. But what you have is the convective term, which is this part, and the pressure part here, right? Multiplied with the surface here, and then you get the force F, force balance equation, which you can derive even from Newton's second law. F is m times A. And so if you derive this for a fluid, you see all of these complicated things here. But now, since this is a vector here, this is a dot product. Rho times Cn is nothing else than the mass flow here. This thing here and this thing here is the mass flow. And C is a vector, and C has three components. C is equals, in this case, Cx, C theta, or Cr and C theta. Cr is equals 0 because we say that we have no radial velocity. We only have velocity in x direction and theta direction. Then these are two vectors, which means that I can make a momentum. I can make the momentum equation here now for two directions, for the x momentum. Okay, so I take this equation and I write it down for an x momentum, and then you see this here. This is the final result. The pressure that is acting on this control surface is P1. Pressure acting on this control surface is P2. And then, of course, I have a momentum at the inlet, which is this C1 times mass flow. And the momentum at the outlet is C2x times the mass flow. Okay? And this is for the axial direction. And this is quite important to know. This here is, so if you look at the gas turbine, for example, for aircraft propulsion, so you have a gas turbine, something like that, mounted on a wing, right? This would be a wing of an airplane, something like that, and this is a gas turbine. And you have a jet coming out here, and you have some air going inside here. The pressure here at the inlet and the pressure here at the outlet, if the gas turbine is built in a nice way for an aircraft engine, the pressures are the same. If the pressures are the same and the area is approximately the same, these terms drop out. Then the only reason why you actually get an axial force on this gas turbine is due to the momentum thrust. This thing is called the momentum thrust. Clear? Because the pressure thrust drops out. But for a gas turbine, it's exactly the opposite. For a gas turbine, for this stage, for turbine stage or compressor stage, it's most of the time the opposite. You are trying to design a turbine stage or a compressor stage in such a way that the axial velocity components are the same at the inlet and at the outlet, which means this minus this will be 0. The momentum thrust on a turbine stage is 0. Can be almost 0. Let's say this is the stator, and then this is the rotor. This is the rotor. The rotor moves like this. And this is the stator. And here you have pressure 1, and you have pressure 3. And you have velocity 1, C1, and you have velocity C3. Velocities, as I showed before, almost the same at the inlet and the outlet, which means the momentum thrust drops out. The only thrust that remains for a turbine or for a compressor is the pressure thrust. Because, of course, in a turbine you expand, P1 is much higher than P2, or a compressor the other way around, so this is the one that remains. And this can be quite substantial. The pressure difference and the area difference here can be very large. So you have very large axial forces on the stator or on the rotor, on both, right? You can have very large axial forces. And that's the reason why, if you look at steam turbines, this is a steam turbine from Siemens, and steam turbines will stay in business for a very long time, even if we are completely fossil free. We will still use steam turbines, or because we are going to use steam turbines for solar power plants, for example, solar thermal power plants, geothermal power plants, or for any other heat sources that we can think of. We're going to use steam turbines in this, or even nuclear power plants have humongous steam turbines that are installed. And so you can imagine that if you have a turbine that looks something like that, and you have several stages here, and you have a very high pressure here. So P1, P2 is much smaller than P1, right? Because you're expanding the flow, and this will be the axis. And this will be the stator, the rotor, the stator, and the rotor, and so on and so forth. And on all of these stages, you will have very large pressure. You will have a very large pressure thrust, which means that you will have a very large axial force in this case. In order to balance this axial force, what they do is that they have a two-flow configuration. Steam comes in this direction, and the steam is split into the left side and into the right side. So you put another turbine like that. You put two turbines facing each other such that the axial forces are cancelled. And that's why we have this two-flow configuration. If you wonder why this is the case, okay? None of the main reason is really to balance or to cancel the axial forces, right? That's why you have these configurations. In low pressure turbines, you will see this very often. Low pressure steam turbines. But you can also do the following. So now we have done the momentum conservation in x direction, but we can also do it in theta direction. If we do this in theta direction, we get an equation that looks like that. This is now the tangential force, F theta. We have talked about Fx before, now we get F theta. And F theta is nothing else than the mass flow multiplied by C theta 1 minus C theta 2. And C theta 1 is which one? Is this component. C theta 1, and this guy is C theta 2. The difference in tangential velocities multiplied with the mass flow gives you the tangential force, of course, because you're turning the flow, right? To turn the flow, you need to apply a force. And that is the equation that we're also going to use to derive the Euler equation, and I'm going to do it a bit quicker now in this case, because you can easily say that if we know the tangential force on a single blade here, we can multiply it with the number of blades that we have on a rotor or on a stator, on a rotor in this case, because I want to calculate the power. Then I can first calculate the momentum. The momentum is nothing else than F theta times radius, right? If we have here the shaft, and here we have the rotor, and this is my midspan plane, as I said before, and this is the radius. This is the radius, and I have a tangential force here. This is F theta. Then the momentum on the axis is nothing else than F times R, or if I use for F theta this equation, then I can write this one here, right? And I have this equation. Then I continue, and I can use m times omega, and I get my power. This is one thing. And then I can also go back to use the conservation of energy and get the equation for power, which is before, the same thing I said before. I assume that Q is 0, that I have no heat losses across here. This is 0. The rotor will extract some work, and then I have W mass flow H total in minus H total out, which is this one here. This is 0, and then I get this equation. Now I have two equations for W. The first one is mass H02 minus H01, and I had the other equation before, which was my momentum times omega, and if I do that, at the end, I will arrive at the Euler equation in a very simple way, okay? And the Euler equation basically tells me now how much, if I know the velocities, if I know my rotational speed. So let's say I know U1 is equals U2 is equals U. If I know the radius and the angular speed, then I can calculate U because it's nothing else than omega times R. Then I know my U. Then if I look at the turbine stage, for example, and I know my C theta 2, C theta 2, then I have the rotor. Then I know my C theta 3, which is most of the time 0, because I said I will have purely axial outflow velocity. Let's say like this. C3, C1, C2. This is my C theta 2. C theta 3 is equal 0. C theta 3 is equal 0. In this case, if the flow is purely axial, then the only part that will actually change my total enthalpy between inlet and outlet is H01 minus H03, because H01 is equals H02 for the rotor, is nothing else than UC theta 2. Okay, this is for a special configuration where the outlet velocity of the stage is purely axial. This is a turbine stage. And you can see it here again. So this is applying the Euler equation to a stage. This is for the compressor, and this is for the turbine. Are there any questions? Not very interactive, but that's how it is this time. Can make it more interactive. The quizzes, in which I have one more quiz here. And the question is the following. And then we can finish. Okay. So you have seen the Euler equation now for a turbine and for a compressor. Using HS diagram, you can connect this part here, and using the velocity triangle, you will get this part. So you connect the velocity triangles with the 10 enthalpies in the HS diagram. I have shown you how to write the detailed HS diagram here for the compressor and for the turbine here. And the question now is the same as or similar to the question we had before. So I leave this one here. And so the question is now, suppose the rotational speed U increases by a factor 2. How does the power of this turbine change? Okay, and then please scan this QR code, and you should be able to get the question on Google Forms. Then you have several answer possibilities. Suppose the rotational speed of this turbine, this is the stator and the rotor. The rotational speed of this turbine increases by a factor of 2. The rotational speed by a factor of 2 increasing means this one and this one. My new U is this value. This is my new rotational speed. So I have increased the rotational speed by a factor of 2 for this turbine configuration. How will the power change? Will the power decrease? As you can see here, and if you go to the Google Forms, I think it's decrease or increase, I don't remember. Decrease, B, increase, C, stay the same, and D, what is D? The P is equal 0. Okay, I have 17 responses, 19 responses. 22. Hmm. 26 responses. 27. I will wait for a bit. Okay, so I have a turbine. I have a certain rotational speed as it is given here. This is the starting configuration. Everything starts with these velocity triangles that you can see here. So I have designed it in such a way that I will get velocity triangles that look like this here. But now I take the same turbine and I rotate it twice as fast. What will happen to the power? The power that I will be able to extract at a rotational speed which is twice as high. I have 40 responses. We still have 4 minutes, but I think I should also explain what happens. "41 responses. "42. The answer to all the questions. 42. Okay, then I will show you the answers you gave for this question. And I will slide down 42 responses. And what you see here is only 3 people got it right. Does the power increase, decrease, remain unchanged, or become zero? So if it becomes zero, of course, here there's a certain power that I can extract. So if it becomes zero, it also decreases. So maybe this was a bit of a tricky thing. You can have multiple answers that are correct here, right? Because it has to decrease to get to zero. So you need to check both, decrease and become zero. And only 3 people got this right. Most of the people actually thought that if I turn the turbine twice as fast, by unchanging the by not changing the mass flow. I've also said again, as before in this previous question, the mass flow is not changing. Okay, the mass flow stays the same. Of course, if I push more mass flow through, then maybe I can extract more work. But if the mass flow stays constant and I rotate the turbine twice as fast, then the power will decrease, and in this case here, it will even become zero. Why? And this thing is called the runaway condition. New share. Let me go to this one here. Yes. No, I don't have the solution here, but fine. Let me draw the solution here. What happens is that I increase the speed twice. I get a new C2. Which is a new W2, so a W2 prime, right? C2 is unchanged, has not changed. W3 stays the same. The speed goes up by a factor of 2. And now all of a sudden I get a C3 that looks like that. This is now my C3 prime. and this is C theta 3. C theta 3 is the same as C theta 2. So C theta 2 minus C theta 3 is equals 0, and the power becomes 0. Ideal. Okay, I didn't talk about losses here, but you can see that if I, in this case, if I assume that the flow doesn't separate like crazy, and the flow simply follows the blade angles, then if I increase the rotational speed of a turbine by not changing the mass flow, I decrease the power that I extract. And this is also something that is called the runaway condition. Imagine you have a turbine that is connected to a generator. The generator produces electricity. All of a sudden, there's some bug in the network, and the generator doesn't give the resistance to the turbine anymore. So there's no braking force from the generator to the turbine because the network has crashed, which means that the generator has no resistance to the turbine will start spinning faster, and it will reach a condition when there's no power extracted. And this is called the runaway condition. And in this case, it's twice the speed as before. Okay. Are there any questions? Otherwise, we are over time now. It's 31. If there are questions, please put them into the chat, and then I can discuss the questions with you. Otherwise, I can also, if you have questions, we can also discuss them next time, because I will continue on this topic, and then I will continue with the design parameters and show you how design parameters are used to actually design these kind of stages. Very simple also, 0D basically. Okay. If there are no questions, then I would thank you, and then see you on Friday morning for the next lecture. Thank you. Bye-bye.
Thank you. Nice evening.
Good evening.
Thank you.
Thanks.